Hello. Hopefully you'll all be able to hear me, and welcome to Rothamsted's research page. Here today we are going to be talking about genetic modification. So hopefully that's where you're supposed to be, in the right virtual room. And if you're not, I really encourage you to stay because I think we're going to have a fascinating chat. So I'm Madeleine Finlay. And for this session, as I said, we're going to be talking about the genetic modification of food, its past, present, and future. It's been 30 years since the first genetically modified crops were created, having been met with both hope, trepidation, and dismay. And whilst public acceptance has grown, better, cheaper, and more environmentally friendly GM food is yet to reach our plates. In Europe, we mostly don't grow GM crops, but we do import thousands of tons of GM soya from the US. We're allowed to grow seeds whose genes have been randomly mutated by radiation, but not those whose genes have been specially altered in the lab. Yet, lab work carries on and discoveries continue. So why has the promise of genetically modified food failed to materialise? Will we see advances in the science and the regulations to match in the next 30 years? In this session, we'll hear from two of the leading scientists developing new applications of GM for human health and sustainability. Professor Johnathan Napier, a pioneer in plant biotechnology and an advocate for the power of GM foods to deliver for the public good. And Dr. Nigel Halford, a crop scientist and expert in the world of genetically modified crops. Johnathan and Nigel will be giving their recollections from a bumpy 30-year journey and their hopes for the future. So I'd first like to welcome Johnathan to our stage. Hopefully, Johnathan, you are there. Hopefully, Johnathan will be joining us in just a second because he is going to be telling us about his fascinating research on camellina trials. So we're looking forward to that, and hopefully he will join us in 2 seconds. So it seems as if Johnathan may not be ready yet. I think he may be lost somewhere in the virtual ether. It happened to me earlier this morning. Doing technology, in the current climate is tough. So hopefully we'll move on to Nigel first and come back to Johnathan. So Nigel, are you there to join us on the stage? Hello, Nigel. Nice to see you.
Hello, are you hearing me okay?
I'm hearing you absolutely fine, and I'm glad you're doing this. And so, Nigel, I've mentioned kind of the idea of GM crops and kind of looking for particular characteristics. But in fact, the kind of work that you do is actually focused on reducing a characteristic. And that's the accumulation of acrylamide, which is a carcinogen or a substance that promotes the formation of cancer. Now, I haven't heard of acrylamide, so perhaps you could tell us exactly what that is and how it ends up in our foods.
Well, acrylamide is not in plants or in our crop products, but it forms during cooking and high temperature processing. So things like frying, baking, roasting and toasting. And it forms from an amino acid called asparagine. It's just one of the standard protein amino acids. And it's not when the asparagine is incorporated into proteins, but it's when it's in its soluble free form in the cells. And unfortunately, plants do seem to accumulate quite a lot of free asparagine. And then that gets converted into acrylamide during, as I said, cooking and processing. So we're looking at ways in which we can reduce asparagine accumulation in crop plants, and specifically wheat grain at the moment. And we're using gene editing. So we're using CRISPR, which people may have heard of, which has a number of being used in medical applications as well. So we're using it to knock out one of the genes that encodes an enzyme called asparagine synthetase, and the name suggests, that is an enzyme that makes asparagine.
And just to kind of give us some of the background to this project, now acrylamide, which comes from this asparagine gene that you've been telling us about. Now, the EU brought in some regulations about the amount that's allowed in packaged foods, and is looking at imposing maximum levels, at which point anything above that would be illegal. So just tell us about kind of where we are with acrylamide, what's allowed and what's not allowed, and why you're working on this project.
So acrylamide was actually only discovered in food in 2002. Quite a shock for the food industry and also for regulators. And it's a difficult issue, not only for the industry and the whole supply chain, but for regulators as well, because basically a carcinogenic compound, highly undesirable in food. And yet it forms some similar pathways, chemical pathways to the colours, flavours and aromas that we associate with fried, baked, roasted and toasted foods. And it's forming from precursor asparagine. You also need sugars like glucose, fructose and maltose, and they're naturally present in crop plants, obviously. And so difficult issue for them. And at the moment, what we have in Europe, and really the European Union leads the way on regulation on acrylamide, we have what's called benchmark levels. Now, they're not limits, and they're not safety limits, nor are they safety indicators. They're more what the European Commission believes the industry can achieve. But in the last set of regulations, which came in a couple of years ago, there was an explicit threat from the Commission to set maximum levels. That's levels above which it would be illegal to sell a food product. So obviously that would be a difficult situation for the food industry to deal with. And we understand that process of maximum levels is already underway in Brussels. So it's very important that the food industry and the supply chain is ready to meet, the demands of complying with those regulations.
And we're going to get on to your project and all the work that you're doing to try and reduce the buildup of acrylamide in the foods. But I mean, at the moment, bearing in mind the EU is looking to put in these restrictions, what other methods do food producers have in order to reduce this without GM? Is there much that they can do at the moment?
That's an important question, because I think people shouldn't see GM, or in our case, gene editing, which is kind of the next thing after GM. They shouldn't, it's not used in isolation. It's used together with a whole load of different things. And whilst advances in GM and gene editing have been going on, there's also been advances in crop genomics, which have greatly facilitated what you might call traditional, conventional crop breeding. And then you have something else you alluded to before, which is the old-fashioned random mutagenesis. That's another technique we're looking at as well. So we're using lots of different techniques, and I think in the video that's coming up, you'll also see someone we're looking at different genotypes of wheat, different varieties of wheat, and also what can be done by farmers at the agronomic level. And then there's a whole raft of measures taken by the food industry itself at the processing stage. However, our kind of analysis of the improvements they've made in processing suggests that there's been a levelling off since about 2011. So we think the big gains from processing have already been made. And of course, there's only a certain amount you can do before your crisp isn't a crisp or your bread isn't bread, So a certain amount we can do there. And we want to make it easier for the food industry by providing them with raw materials, in this case, wheat grain, with much less potential for acrylamide to form.
And we're going to watch a video in a second about the research that you're doing about working with this asparagine amino acid and reducing that in foods. But first, I just wondered if you could kind of give us a very brief idea about the process and how this works and exactly what you're doing in the lab. Now, I know it's very complicated, but perhaps you can give us a sort of brief overview of how this research actually works.
It is complicated, and also it's an evolving technology. But the way we're using it again, it's CRISPR. We actually do make a genetic modification to wheat. And we used to introduce a gene that's making a nuclease. That's an enzyme that's going to introduce a nick in the DNA. And we also introduced what we call a guide RNA gene. So the guide RNA will interact with the nuclease and it will direct it to the gene that we want to knock out, which is a gene called asparagine synthetase 2. Once there, the nuclease will introduce double-strand breaks in the DNA. And because the repair process is error-prone, you get a number of plants coming through that process with small mutations in it. And we look then for mutations which will knock the gene out, render the gene dysfunctional. So we no longer have a functional ASN2 enzyme. That's basically it. But we can then cross the GM bit away, and that's a crucial difference. So at the end, we get a plant with a target. It might be a very small mutation targeted to a single gene. No GM, no foreign gene, no extra gene. That's gone. And we have a plant with an edit in it. And that's how the technology works. And then we are at the point now where we're just going to start a project where we hope to do field trial with some very low asparagine CRISPR wheat line. So a very exciting point in the project, but still an experiment. So we still have to have all these other things going on as well, because it may not work. We put them in the field, and of course we don't know how they'll perform. So we still have to do a lot of work here.
Now, I have many questions about taking your work from the lab into the field and about this experiment. And I'm sure our audience will have lots of questions too. And I encourage them to put them in the chat box below. And we will try and come to as many as we can. But as I said, we've got this video of some of the work in the lab. So perhaps our technology master behind the scenes is able to play that video for us now.
So it's quite a simple process. We're going to take one seed, we're going to put it in there in a mortar and pestle, and then we're going to crush them up with liquid nitrogen. We're using liquid nitrogen, one, because it makes it easier to crush them up, but also because as soon as we start crushing them up, we want to freeze the amino acid profile inside the seed. So everything here has got to be kept as cold as possible. So as soon as we start the destruction process, there could be degradation and it could change results. So once this goes in, we start crushing, everything's got to be cold. Ready? And we do them one by one like this because we do single seed amino acid testing. So instead of taking a whole bunch of seeds and grinding them up together, we actually look at the amino acids in each individual seed. Okay. Right, so that's all the liquid nitrogen gone. I'm just going to cover it just like this, just in case on those initial grinds, things decide to shoot up. We want to grind it up as finely as possible, really, so that we can kind of extract everything that there is inside the seed. So not missing anything, we can get a really accurate picture of the amino acid profile inside the seeds. And then, this is for seed powder. You get a nice little seed group, and inside that will be our amino acids and stuff. That's one done. And then those will go through a couple of other rounds of extractions, again in methanol and chloroform. And then at the end we add water, we take the aqueous stage of that and run that on HPLC, and we can see what's inside it.
Fantastic. So that was Sarah Raffan, and thank you to her for showing us a fantastic lab technique. Now, as you mentioned before, we can see in that video that it seems like the scientific lab-based process is reasonably well established, although I'm sure there is plenty of work and development going on. But what about some of the challenges of taking it from the lab and putting it into the real world, the field, where there are so many variables?
Well, that's exactly why you have to do it. So, the effects we get in the lab, and of course, these have been grown under glass, these plants now, for several generations. But of course, until you get them out in the field, you don't know how they're going to perform. You don't know if the asparagine levels are going to be still going to be low. You also don't know how they're going to be, what's the yield going to be like, what's the protein content going to be like, what's their disease resistance going to be like. So, I mean, even the first field trials will be a first step. So, you know, it's a long process to get something from, you know, just from gene characterization and showing what the gene does and identifying the gene that you need to target to actually doing the gene editing. And then you've still got years to go to get them into a breeding program. And I think the field trial we're proposing, I think it's the first CRISPR wheat field trial, certainly in the UK, that I'm aware of in the public sector in the world, I think. I may be wrong, but, you know, it's which shows that it's not an easy thing to do to get them to that point. And, of course, now in the European Union, and we're expecting European Union rules and regulations to roll over post-January the 1st until the UK government has time to reassess them. We have to treat these plants as if they were GM plants, even though, as I said, they have no GM element to them. And so we have to apply for a license to grow them. We have to apply to DEFRA for that. There'll be all sorts of conditions over running the field trial, which we'll have to comply with, including what happens to the trial site afterwards. So everything that we know which goes on around GM field trials will apply to this. So quite a challenging thing, but very exciting thing to do as well.
Wonderful. And we're going to return to some of the questions around the future of GM and gene-edited foods and some of the regulations and where we go next. But for the moment, Nigel, I'll hold us there. So thank you very much for talking to me about your project. And I'm going to invite you back later. So again, anyone watching, if you've got questions for Nigel, do pop them in the chat box below. But for the moment, I'm now going to welcome Johnathan to the stage. So hopefully Johnathan has now made it on to our session. Johnathan, hello, hi.
Hi, can you see me? Can you hear me?
I can indeed. We're glad to have you. So, Johnathan, now that you're here, I'm looking forward to talking to you about your project. Now, we've been hearing from Nigel about his work trying to genetically edit food in order to bring down this carcinogen in line with EU regulations. But I just wondered, what are some of the other reasons why we might want to develop GM foods? Why might we need them in the future?
Well, I mean, I can give you the example that we've worked on for quite a long time, which is to use GM to provide nutritional enhancement. So to make a plant more nutritious than it would be normally. And that's something that, you know, we've focused on in the case of our engineering plants to make omega-3 fish oils. And omega-3s are really health beneficial, and they've got proven benefits to our cardiovascular health. There's also a whole environmental reason why they're a good thing to do. But, you know, that is, you know, that's a complicated trait to engineer into a plant. You can't do it by natural breeding. You can't do it by gene editing, in fact. You can only do it by GM because you're putting a whole new capability into the plant. So in our case, you're putting 7 new genes into the plant to give them this new fantastic ability to make omega-3 fish oils. You know, and that's just one example. But you could think of, you know, there's lots of other examples. You know, our colleagues at the Johnathan have made tomatoes that are black, full of polyphenols. You know, people are making wheat plants that are full of folic acid. You know, there's lots of things to do, but they're usually more complicated than some of the other traits that people have tried in the past.
And just very quickly, I wanted to, for those of us who, including me, may not, you know, be an expert in this field, both of you have kind of talked about the difference between GM, genetic modification, and genetic editing. So I wondered if you could just quickly give me a very brief explanation of the difference between those two.
See, it's really easy. So in the case of GM, you know, so you could use my example of omega-3 fish oils being made in plants. You're adding in new genes. So you're adding, if you like, foreign DNA. So we're adding genes from algae into our plants. So we're putting in extra DNA. In the case of gene editing, you're usually removing DNA. So you're taking DNA away. So it's really as simple as like adding or subtracting. And that's the sort of, to me, that's the simple way to think of it. So, so GM adding DNA could be foreign DNA, could be, could be other plant DNA, gene editing, taking it away.
And as you said, your project is genetic modification and trying to include omega-3 in these plants, or the production of omega-3. And this is, you're trying to do this in camellina. So tell us what camellina is.
So camellina is like the sort of cousin of oilseed rape, canola. So it's an oilseed plant, and it used to be grown a lot in Europe, probably up until about 100 years ago. It was the most popular oilseed crop that people grew. You can find traces of it in Bronze Age earthenware utensils. Man has been using it as a crop for thousands of years. And no, we started using it because it's really easy to genetically modify, and it's got a nice oil profile, and it also is already used. People use the oil profile in aquaculture, in fish farming, and we're interested in fish farming, and we may not have time to talk about that, but omega-3 fish oils are used a lot in fish farming, and camelina oil has some attributes that make it really useful for aquaculture. So it's not grown very widely in Europe at the moment, but it's grown quite a lot in Canada and the US, and we would hope to be able to grow it, to grow much more of it in the GM form in the future, because we think having a sustainable source of omega-3 fish oils would be a really good thing. So you don't have to rip them out of the oceans, you can grow them in a field.
And we're about to see a video of the process of putting this, putting omega-3 or including omega-3 in camellina, and we'll see the process in the lab. But just before that, I wanted to ask kind of where the project is at the moment. How long has it been going on, and where are you at the moment? What should we expect to see from it next?
I started this project around about 1994 or 95, and it's my birthday today, so I'm 58.
Happy birthday!
So I can't do my normal joke, which says that when I started that project, I must have been 13 or something. But the take-home messages, we've been working on this for about 20 plus years. But where we are now is pretty advanced. So we're much further down the line than, say, for example, Nigel was talking about. So we've done 6 years worth of field trials of our GM material for exactly the reason that Nigel says. You have to do these experiments in the real world to demonstrate that technology works in the real world. It's good sitting in a lab. We need it to work in the field, in the real agricultural environment. We've done field trials in the US and in Canada and in the UK. We've done animal feeding studies. We've done human feeding studies. So we've moved quite a long way with the technology. So we know it works, and we know that it's safe, and we know that it would be viable and economically useful. But there's still work to be done. So 20 years in developing a technology in agriculture is really quite a comparatively short period of time. You think about how long plant breeding takes and all of these things. So we're working as hard as we can to move things as quickly as we can, but it just takes time. But I'd like to think we're getting to a point where the technology will stop being my baby, and it'll be a teenager that leaves home, if you think of it that way.
And we're going to come back to where the technology is going next, and have a chat with both you and Nigel about that. But now we've got a video that we can watch of seeing camellina in the lab. And if you want to maximize the video, you need to click on the video feed, and then if you want to minimize it, again at the end, once again click on the video feed. So hopefully again we'll have this video of camellina and omega-3 genes being put in the lab.
We isolate the DNA from the algae, which are making the fish oils, and purify the DNA so we can introduce it into our GM plants. The individual DNA fragments are then purified and cloned into a vector which allows us to introduce them into agrobacterium. The bacteria containing our algal genes grow overnight, and we can pick the colonies that contain these algal genes and grow them in liquid culture to help us move them into our plants. To introduce the algal genes into camellina, we just have to dip the flowers of a plant into the bacterial solution. The bacteria we're using here is Agrobacterium, which naturally transfers genes from itself into plants. When they've set seed, we can identify the seeds that have been genetically engineered by looking for a red fluorescent protein that we introduced as part of our engineering. But we can check that they really do have the fish oils by running them on this instrument, which is a gas chromatograph, to look at the fatty acid profile of our seeds compared to regular non-GM camelina plants. And from this trace, you can see that the wild-type camelina does not contain any of the fish oils that we've engineered into our GM camelina plants. The large peaks that you only see in the genetically modified forms are the specific fatty acids, these omega-3 fish oils that we've been trying to engineer into our plants.
A fascinating insight into the multi-stage process of getting omega-3 into the camelina plant there. And one of the things that kind of struck me watching that video is it's clear that the science, I mean, as you said, over the past 30 years has really developed. And, you know, something like CRISPR this year winning the Nobel Prize, it's very well understood, and it's something that we can do. And there are GM plants available that are largely grown in the US that kind of look at disease, pest resistance, things like that. So why haven't we seen plants of the type that you're trying to develop that's, instead of it being about pest resistance and things like that, that it's about nutrition and bringing these benefits for us humans?
Yeah, I mean, that's a great question. I mean, some of it's to do with the complexity of the trait, you know. So like I said, we have to put 6 or 7 or 8 genes into the plant to engineer the omega-3 trait, and some of the other nutritional traits are quite difficult to engineer as well. I mean, some of it is just, I think, a lot of the work on developing nutritional trait has been done in academia or in publicly funded labs, whereas the work that was done on the herbicide tolerance traits and things was done in privately funded labs. And the simple truth is, it takes, as I've already alluded to, it takes a long time to develop a GM plant, but it also takes a lot of money. And it takes a lot of money to get through the regulatory approval system. Now, I'm all for the regulatory approval system. I think it's really important that the consumer is confident that they have safe and well-tested, food to eat. So you have to find the right level of regulation. But those in the approval process, even in places like the US, where people think the process for approval of crops, of GM crops, is straightforward and easy, it will still take several years. It will still cost you millions of dollars. So that's a challenge, you know. So if you work in a university or an institute like we do, it's like, well, how are you going to bring that technology to the table, literally to the table? You know, because how do you find the money to pay for all the regulatory approval costs and things? And these are the challenges that we have. We're up for these challenges because we believe the technology we have is really useful and can be beneficial and bring better health and have a better impact on the environment. So you have to work out a way to bring that stuff forward. But you're right. It's a challenge to see, why does it take so long? And the problem is, it's a little bit worrying that it appears to take so long.
And I think part of the one of the things that you touched on there, talking about the regulations, all of this is based on concerns around safety. And, I think it's one of the main concerns that you hear from people who are cautious and worried about GM foods, is the idea of it being safe. And Nigel, I'd like to ask you this question, because obviously you are working on a plant that is hopefully going to make food more safe for people to consume. And so I wanted, you've been working on this for a long time. whether you could comment on kind of safety and regulation and where we are, and that interplay between safety and regulation here in Europe.
Okay, well, I think the first thing to point out on GM is it's not a new technology. It's a 20th century technology. It has been in the field and in our food for generations now. So billions of people have eaten GM food. It's widely grown around the world. It's really only Europe and a few other places where it is regulated so strictly that it's difficult to get to cultivation. So my question back there is, how long can we carry on saying it is a safe technology? Well, it's 25 years of proof, I would say, is probably enough. Even so, they're the most intensively studied, analysed, regulated foods that there are. So there are a lot of novel foods come onto the market. GM ones are regulated much more tightly than the others. So they should be safer. If anything, they should be safer. I'd also say there's a scientific consensus that, nothing is risk-free, but the GM is no more or less risky than other methods in plant breeding, all of which involve doing things with genes, mixing them in, bringing, wild relatives into breeding programs. All these things have an element of risk, but they also have potential big benefits. And, I've told you about the potential benefit of our program, Johnathan's clear potential benefit for the consumers. And I would point out, actually, just answering a question you asked Johnathan at the end there are improved food safety examples of GM crops on the market in the US. The acrylamide issue also affects potatoes. There are low acrylamide potatoes, GM potatoes, not gene edited, GM potatoes on the market in the US already. So their consumers have those available and they can make their choices, and our consumers can't. And that really what kind of upsets me a little bit. So I would say to you, how long can Europe go on pretending that the GM revolution didn't happen in crop size? It happened quite a long time ago. And for heaven's sake, let's not make the same mistake with gene-edited plants.
And as you said, there's some way to go with the regulations and also kind of the culture and attitudes towards GM food before we see them on our plates, and probably a lot of us feel comfortable eating them. And in the meantime, people are looking for other alternatives to gene editing or gene modification, and one of those is one of your PhD students, Nigel, who's looking at an alternative way of finding getting low asparagine crops. So just tell me about what he's doing.
Well, that's Joe Oddie's project. Well, I talked right at the start about other things that can be done. Of course, we're coming from the agronomic point of view. There are things processors can do as well, but certainly crop nutrition plays a big part in it. So we've shown that sulfur deficiency, for example, leads to a big accumulation of free asparagine in wheat grain. So we put that advice out to farmers. It's actually been incorporated into the current EU regulations, that they should ensure that wheat has plenty of sulfur fertilizer as it grows. We're continue to look at what Joe's looking at as the ratio of nitrogen to sulfur that is optimum to get the minimum amount of asparagine to accumulate. He's also looking at some of the genetic differences that are naturally out there in wheat varieties and could be exploited to reduce asparagine. And again, it's a point I made earlier. No one's saying GM or gene editing has got to be done to the exclusion of everything else. They are tools in the box, and I think people should be able to use all the tools available to them to improve food safety, to improve sustainability of agriculture, or whatever it is.
Now, I know that we have a video of Joe Oddy doing his project in the lab, which we're going to share, but because time is already against us, unbelievable, these sessions go so quickly, I'm going to actually go on to audience questions first to make sure that we can answer some of our audience questions, and hopefully, if there's time at the end, we'll get ready to watch Joe Oddy in the lab to finish us off. But first off, we've got some audience questions, and I'll put this to you, Johnathan. Elric Mackey has asked, should GM or GE science be an open source to prevent large companies like Monsanto from taking advantage of them?
I mean, that's a great question, and I think in principle, it always sounds great to be able to have an open source approach to any new technology or any technology at all. The problem is the one that I alluded to already, which is that the cost of regulatory approval of these new foods is of millions and millions of pounds, and actually the only way that you can invariably cover that costs of that regulatory approval process is through through a commercial process. So basically, you need to have a way of recovering that cost, because no funder is going to pay. Public funders don't pay for that sort of process. Invariably, the view is that it should be done as a public-private partnership. So the model would be, I should work with industry to develop my crop. And I should use intellectual property to to protect my invention, and that intellectual property can be licensed to a company, and the company can make money, and we can get a return on that. So and that's the model that is used across the planet for all sorts of things, like drug development, the people developing the COVID-19 vaccines and things. That's the model people are using to cover those costs. Now, is that ideal? I'm not sure. But I mean, we have patents that cover Rothamsted's development in the omega-3 space. Why do we do that? Because we're a publicly funded entity, and it is the best way for us to invest to protect the investment of the UK taxpayer in our technology. If somebody could find a better model, that would be great. But invariably, it still boils down to the same thing: is using taxpayers' money. And at the moment, this is why the model that we use. That's a very long-winded answer, but I mean, but it's a complicated topic.
It's a really very difficult one, and I know that people feel very differently about patents and intellectual property when it comes to GM and our foods and our crops.
I mean, I can say it quickly. But people don't worry about the fact that their mobile phone has got 2,000 patents owned by multiple different companies, and and technology companies, whether they're Apple or Microsoft or whatever, could be viewed as very aggressive in the way they roll out their technologies and they protect it. But people don't worry about that, because they can see a benefit and a reason for and a utility. So for us, we have to demonstrate the utility of our technology.
And Nigel, do you have any comments on that?
Well, we're not a seed company, so we don't sell any seed, and there's no, UK collective seed production system. If we are going to get our technology to the market, then we have to work with plant breeders to do it, whoever that is, whether it's Monsanto or anybody else. And we are working with a number of UK plant breeders on our project. Otherwise, the technology would never see the light of day. You would just stay in the lab and the glass house and the field trial, and never get to get further than that.
Which would be a waste of taxpayers' money.
Yeah, exactly.
And we've got a few more questions here, and we've only got 6 minutes left, so I'm afraid I will have to kind of ask for brief answers. But Heloise Hunter has asked us, and again, Nigel, I'll turn to you first. Do you think the regulatory processes have become more or less strict over time?
I don't know. The EU ones haven't changed for some time. Now, the problem is not, the regulatory, in terms of the scientific assessment. I think that works well. So EFSA has an expert scientific committee which assesses what is a lot of safety data that any company has to present to them to get approval of a GM crop. But it then goes to a political committee, and getting that political committee to approve commercial field cultivation of a GM crop is very easy. So what is very difficult, rather, much easier to get approval for import and selling for food and feed. So that is generally what companies apply for now. So although we do have GM maize grown at a fairly large acreage in Spain, that got established very early on, there's been no approvals for new approvals for GM crop to be grown commercially in the European Union for over a decade. And that's just ridiculous. And it can't go on. Something's got to change.
And, looking back over what has happened and looking to the future and the hope that something will have to change, and particularly, with oncoming challenges such as climate change and, a growing worldwide population. And I think this kind of takes us nicely to Flora McMichael's question that we have, which, Johnathan, I'll put to you. And she asks, do you think that it's a certainty that GM and gene-edited crops will be widely consumed in the future?
Well, I mean, as Nigel already said, people have been growing and consuming GM crops for 20 years. So, I mean, the GM crops are being consumed, gene-edited crops, the ones that the few examples that have been regulated and approved are being consumed as well. So, I mean, I think it's that is effectively a sort of closed book. The story is finished on that. That people are consuming GM food. It's just in Europe that we have this slightly sort of schizophrenic approach to it, in that we won't approve it, but we'll allow it to be imported for use as animal feeds. And then when we go on holiday to America, presumably we don't take a month's worth of sandwiches with it. We do actually eat the food that is in the US. So I mean, I'm being facetious, but I mean, it's people. I guess it's sort of. The technology is considered to be safe, and that's not, that's all accepted. The most important thing is, what can we do with it in the future to address exactly the challenges you mentioned, such as, climate change, global population expansion, all of these things, malnutrition. There's a huge problem, not with people being malnourished due to lack of calories, they're being sort of malnourished because they're eating the wrong sort of food and they're over-consuming. So, type 2 diabetes is a pandemic, that affects, nearly 1 billion people on the globe. That's not because people are eating too little, they're eating the wrong food. And that comes back to this nutritional enhancement thing, saying, we should eat a better diet. And it's possible in the case of, omega-3s, that GM is a way of providing those important nutrients to people,
And with just a minute left, Nigel, as somebody who's also kind of working on the nutritional content of foods, I don't know whether you want to comment on that, and also maybe give us a kind of quick view on what your hopes are for the future of GM.
Well, I think the GM revolution happened. It happened last century. I think the gene editing revolution in crop improvement is well underway. And yes, people will be widely consuming gene-edited crops in the future. They are already consuming GM crops. It's just a question of whether Europe wants to join in, really.
Brilliant. Well, I think that gives us a quick tour, but fascinating to hear from both of you. So Nigel and Johnathan, thank you very much for telling us about your research.
Thank you.
Pleasure.
And I hope the audience enjoyed the session. And, I know that sometimes GM researchers have a reputation of being, Frankenstein-esque scientists, but I hope we've dispelled that for you today. It's been a really fascinating chat. And there are many more interesting discussions in Rothamsted Researchers' Room, which will be hosting a number of sessions, including one I'm jumping over to at 3 p.m. on grasslands. And despite the old phrase that it's as dull as watching grass grow, I can assure you this is anything but. We'll be chatting about a new theory of soil, how it isn't just an inanimate lump of mud, how grass isn't just grass either, and the challenges of turning a farm vegan. So I hope to see you then in our next session. But again, thank you very much to Nigel and to Johnathan.
Cheers. Thank you.
Thank
you.